All right, let's begin. We are going to be doing dimensional analysis and some similitude problems today as examples. That material is found in Chapter 8 of your textbook. And I would encourage you to review the information in the book, read through that chapter. It's interesting stuff and it's important. The final exam is going to consist with an emphasis on Chapter 7 and 8. And so it's a comprehensive exam. You can expect problems from throughout the course, but a greater fraction of the points will be earned on the new material that you haven't had an exam on yet. So focus on Chapter 7 and 8 and reacquaint yourself with some of the earlier material as well. Okay, I want to begin with the definition. And an equation that's dimensionally homogeneous is an equation where the units on the right-hand side and the left-hand side of the equation are the same. And so this is the equation that's shown here will allow you to calculate the flow over a weir. A weir would be like a barrier that water's flowing over the edge of something. And what that equation says is that if you have some energy loss parameter C, which is the fraction of energy that's lost, and the length of the weir, and you know the height of the water above the weir's surface, then you can calculate the flow rate. And so if we try to decide whether this is dimensionally homogeneous, we could look at the units on the left-hand side. So we know flow rate has units of cubic meters per second, or cubic feet per second, and so that's length cubed per time. Those are the units. And on the right-hand side, we've got no units associated with C. That's a unitless energy loss parameter, but the length of it would be meters and so on, and so that has units of length. Inside the 2G, G has units of meters per second squared, and so that's length per time squared. But now, since it's under a square root, what's that effectively is length to the 1/2 power and time to the 1 power. And now this final term, height, which is a distance parameter to the 3/2. So if we add up the first length, and then length to the 1/2, and then length to the 1.5, then in total that's length cubed, and then down to the denominator is time. So this is a dimensionally homogeneous equation. The units are the same on both sides, and oftentimes an equation being dimensionally homogeneous is a clue that it's a fundamental equation that's based on observations in physics, based on the laws of physics and sort of the fundamentals of physical behavior rather than an empirical equation. The empirical equation is kind of the opposite of a fundamental equation, and oftentimes empirical equations are not dimensionally homogeneous, which means that there's some sort of like a strange fudge factor in there, some just like value that makes it all work. That's like a coefficient that relates observations that were taken in a lab with some formula that kind of predicts the behavior most of the time. And so can you think of an equation you've encountered before that's non-dimensionally homogeneous, that the units on the right-hand side and the units on the left-hand side may not necessarily be the same? Hazen-Williams equation. Very good. That's right. There will be a lot in hydraulic engineering where the units don't work out, but we still can get good performance out of an equation like that. We can't dismiss it entirely. Usually we rely on these empirical equations because there isn't a simple fundamental explanation that we can quickly and reliably use for predicting the behavior. So that's why sometimes we end up with these non-dimensionally homogeneous equations. So dimensional analysis includes that, an awareness of units. It also includes the use of models to predict full-scale behavior. And so an example of using a model to predict full-scale behavior would be in the aerospace industry, where it's very common to have models made out of clay, or these days they can 3D print a model very quickly and then test its performance in a wind tunnel. And the reason why having a model to predict the full-scale performance is such a great idea is it can be very costly to make a full-size airplane. And so if you're going to make some small adjustment to the winglets at the end of a wing, you'd want to know in advance through maybe numerical modeling or physical testing that it's going to have a beneficial effect before you take the time to install it on an aircraft where maybe safety is an issue, as well as fuel economy and the need for high speeds to get from place to place. And so models are an important part of car design, aircraft design, and actually in civil engineering as well. We use physical models to predict the behavior of things such as dams or pipe networks. There's a huge number of applications where dimensional analysis will allow us to find out the required size of things. You're probably already acquainted, maybe as a kid you put together a model airplane or a model car, and on the boxes when you buy those models they tell you what the scale is. It's a ratio of 1 inch on the model equals so many number of inches on the full scale thing. And so that's talking about the ratio of the sizes, but oftentimes it's not just the ratio of size that's important, and we'll get into that in just a minute. Here is a picture of a physical model that was just kind of recently retired. It was in operation for a long, long time, and it was a very important physical model, but just in the last few years it's been replaced by sophisticated computer-based models to where it's more of a museum piece now rather than being as important as it used to be. So this is a model of the San Francisco Bay Area, and it's huge, 320 feet by 400 feet. This is a look at that model from a different perspective. Let's actually watch a quick video clip to give a little bit of background information about this model and why the government agency would take the time of building a cute little model of the San Francisco Bay. It's not for the same reason that guys go into their basement and make models of little trains with the conductor and the mountains and the smokestack and all that. It's different motivations when it comes to the Army Corps of Engineers taking the time to simulate the San Francisco Bay. Get that link. Okay, so the purpose of building this model back when it was originally conceived was to test an idea. The idea being, should we put a couple of dams across the San Francisco Bay to turn it into a freshwater reservoir rather than what it is now is a mixture of the Pacific Ocean interacting with several rivers and estuaries that discharge into the bay. And what they were able to determine through the analysis is that it would have had a horrible effect on the habitat of fish and birds and small animals, and that it would have really interrupted an important ecosystem. And so it was, as he said, the idea was rejected, and the real value here is that they can find out quickly what's happening with the bay, the compression of time. And so he mentioned one of the applications is in an oil spill. And so they can release a liquid into the bay model and find out how quickly it's distributing and where it's going to go, and very quickly assess threats and then take that understanding of what's going to happen and craft a reaction strategy in the real world to what the model predicted what would happen. So that's just an illustration of how physical models can be so useful in predicting behavior and allowing us to make engineering decisions.
Since this is scaled down so small, would they have to use like a lighter fluid to compensate for the...
No, that's a good question, and we're going to get into when you are trying to have what's called dynamic similitude, which is a scaling of the forces rather than a scaling of size. I think since they're continuing to use water, that's why they put in those copper strips, was because they needed additional resistance that the fluid itself couldn't provide.
I'd assume San Francisco Bay is pretty salty too, so...
Mm-hmm. Yeah, a little bit. Seawater has a unit weight of about 1.0. The specific gravity of seawater is very close to water. It's just slightly more dense, like 1.03 is the specific gravity. So, Okay, so there's two types of similitude that we're going to talk about. And the first is the scaling of size, which many of us are already acquainted with, the idea of a model that's maybe, in this case of the San Francisco Bay, they're saying the horizontal distances are 1 to 1,000. So in geometric similitude, you'd have a prototype, which is the full scale, and a model, and they're identical in all of their features except for the sizes are just ratioed down. So the proportionality exists between the width is the same ratio as the ratio of the lengths, and the heights are the same ratio. But the problem of making a model that follows geometric similitude is that the model ends up being too strong. And think of it this way. Some of you when you're young probably had little Matchbox cars, right? You know, the toy cars they sell at Walmart for about $1. They're really strong. If you take one of those Matchbox cars and you take it to shoulder level and drop it on the ground, nothing's going to happen. But think about if you took an actual car to a similar height and dropped it. It's not going to do as well, right? And so it's really the forces that need to scale rather than the sizes. And so to simulate the behavior of an actual car by dropping a model, we'd have to maintain not geometric similitude, but we need to focus on dynamic similitude. And so dynamic similitude is where we are taking models and we want to make sure that the masses and the forces have the same ratio between the prototype, which is the full scale, and the model, which is the small scale. And so in terms of fluid mechanics, one of the ways that we ensure dynamic similitude is ensuring that the Reynolds number matches between the model and the prototype. And so we want to, for example, look at flow through a small pipe versus a large pipe. If we want to have dynamic similitude, then we'd ensure that the Reynolds number is the same in both of those cases, and then we can ensure that the forces acting on both have been scaled appropriately for dynamic similitude. We'll do some calculations related to that in just a minute. So to maintain the proportionality of forces, sometimes if you are testing let's say a small-scale wing in a wind tunnel, then maybe you'd have to have extremely high velocities in order to maintain the needed proportionality in forces, like unreasonably high fluid velocities if you were using air in a wind tunnel. And so to get around those extremely high velocities that maybe would be required, some of the ways to work around that would be to increase the density of the air inside of a wind tunnel by pressurizing it, or if you cool the gas so that the density is increasing because cooler gases have higher density, or sometimes you could use gases other than air that have a higher density, or you could even switch to a liquid. And so testing a wing inside of a water tunnel instead of inside of a wind tunnel. Well, let's just test out the idea of scaling the Reynolds numbers so that they're equal with the idea that we have a blimp. The full-scale blimp is going to be 50 meters long from end to end and 5 meters in width. And we want to study how it would behave inside of a wind tunnel. And so we have to build a model that's 1 to 10 scale, meaning that the model is going to be 6 meters long instead of 60, and it's going to be ½ a meter wide instead of 5 meters wide. So if we anticipate that the prototype is going to fly at 10 meters per second, then what wind speed should be used inside of the wind tunnel? Now, the way that we set problems up like this, we say that the Reynolds number of the model should equal the Reynolds number of the prototype. And remember that Reynolds number is velocity times diameter divided by the kinematic viscosity of the fluid. And so the velocity of the model times the diameter of the model times the kinematic viscosity, divided by, the kinematic viscosity of the model, should be made equal to the velocity of the prototype, the diameter of the prototype, and the kinematic viscosity of the prototype. So what you should do here is rearrange to solve for the unknown. And here it's asking what wind speed should be used in the wind tunnel. And in both cases, the prototype and the blimp are going to be going through air. And so you can either look up the kinematic viscosity of air, or in this case, since they're going to be equal, then you can cancel it out. But I'll just pause for a moment so you can put the numbers into the equation, rearrange the equation, then substitute the numbers in there, and find out what wind speed should be used inside of the wind tunnel. All right, so since this is air in both cases, we can cancel out the kinematic viscosity parameter from the equation. And it's going to be, if you don't cancel it out, both in the numerator and in the denominator. All right, so the size ratio is 10 to 1, so that means the length of the prototype is 10 for every 1 unit of length in the model. So that means that if the prototype is going to be flying through wind at 10 meters per second, then the model has to experience wind at 100 meters per second. And so the way to think about that, remember I said in the case of the Matchbox car, the little Matchbox car is too strong relative to its size. And so if you want to simulate a crash, you have to give it much heavier forces on the small model. And so in this, the analogy is that since it's smaller, it's going to be more rigid, less likely to deform under the winds of 10 meters per second. So you'd have to give it 100 meters per second to maintain that same Reynolds number proportionality. Any questions about this first example? Okay. Well, let's consider a similar case. This is going to be a little bit more complicated, though, because we want to simulate oil flowing through a pipe with water flowing through a pipe. Okay, so here we have that water is going to be flowing through a smooth pipe that has 15 centimeter diameter, and it's going to be going at 2 meters per second. So that's going to be out in the real world. But to understand how it's going to behave out in the real world, we want to simulate that by using water flowing through a smaller pipe, water at 20 degrees Celsius. And the kinematic viscosity for water at 20 degrees Celsius, let me write that on the board, is 1 times 10 to the minus 6 meters squared per second. Okay, so the question is what velocity should we have going through that pipe so that it's dynamically similar to the situation of the oil going through the pipe at 2 meters per second. Same kind of idea as the previous problem. Okay, we're comparing oil flowing through a pipe, a big pipe, with water flowing through a smaller pipe. So we've got different velocities, different diameters, and different kinematic viscosities of the fluids. We want to make sure that the Reynolds number of one case is equal to the Reynolds number of the other. And ensuring that will allow us to model the oil pipeline with a smaller water pipeline. And so it turns out that the water should be flowing at 1.5 meters per second. Because although the water pipeline is smaller, the water has a much lower viscosity than the oil viscosity. And All right. So as I was saying, what's pictured here is water flowing through an orifice that's inside of a pipe, and the water is going in the opposite direction that you'd normally expect water flowing through an orifice like this. And so, if we wanted to understand how this behaves, what are the head losses through such an orifice inside of a pipe where you've got flow that's full, you'd have to do some experiments, and you could create a series of experiments to increase the flow rate and measure the head loss through a fitting like this. The numerical solutions of a problem like this, maybe to begin with, wouldn't be very accurate. And so the physical testing would be a more reliable way to predict how this would behave out in the field. If you had a small-scale model, then you could predict the prototype. You couldn't do it necessarily on a full scale. If you wanted to have a big one of these on a natural gas pipeline, you wouldn't want to put it in a production environment without understanding first how it behaved. And so the question is how do you relate the model of something complicated like this where you've never seen before and you're not exactly sure how the parameters relate to each other to the real full-scale thing? Well, there's an approach that can help start to shed some light on how a model and a prototype interact with each other by combining variables that have dimensions to them and forming dimensionless groups that are called pi groups. And it helps you to proceed with experimental design. And so just an example of a dimensionless group is a Reynolds number. Here's one version of the Reynolds number: density times velocity times a length parameter divided by viscosity. We've already been using other versions of the Reynolds number today where velocity times diameter divided by kinematic viscosity. It's a unitless group. And unitless groups are the key to dimensional analysis. You can see that, by the way, there's three base kinds of units. There's length, mass, and time. All of the other units in the world are derived from those three main foundational units: length, mass, and time. And we could reduce every unit that's out there into some combination of length, mass, and time. So in the case of Reynolds number here, density, which is kilograms per cubic meter, has units of mass divided by length cubed. And velocity, which we measure in the SI system as meters per second, is length per time. And here in the Reynolds number, the length is meters, which is length. And the viscosity of Newton seconds per meter squared, well, we can break the newtons down into kilogram meter per second squared. So that's the definition of a newton. And then if we cancel out the All right, so yeah, part two of this lecture is not going to sound great. Okay, so we were talking about unitless groups, and this zero with the brackets around it means a combination of units, a combination of variables that has no units. So the Buckingham pi theorem is an approach to creating these unitless groups so that you know how to gather experimental data to form new equations. And the Buckingham pi theorem says that there should be a certain number of unitless groups out there depending on how many variables are having an effect on each other. So like the variables that are helping to predict the behavior, and then M
is how many dimensions are among those variables, with 3 being the maximum because there's only length, mass, and time. So if you calculate n minus m, then that'll tell you how many dimensionless groups should exist. And putting together, knowing what the combination of pi groups is a process that's kind of a little bit like a puzzle solving, like a problem solving or a puzzle. So just to illustrate what I mean by that, if we take the case of a sphere that falls downward in a fluid, then we want to have some sort of an equation that says what is the relationship between velocity, density, viscosity, and diameter. So those are all parameters that we know influences drag force, but we don't know what the equation is. Like if we wanted to predict the force of drag that a sphere experiences as it settles downward through the fluid, just through observation over time, we observed that if the fluid viscosity was high, that the sphere would settle slower. You know, like a marble is going to fall down through water a lot more easily than it's going to fall downward through glycerin, because glycerin has a higher viscosity. Or in the case of diameter, a large diameter sphere would fall downward more slowly because it experiences more drag than does a small diameter sphere. And so velocity, viscosity, density, all those fluid properties we know somehow affects the drag force that a sphere experiences, but we don't know how it fits together. So if we applied the Buckingham pi theorem to that, we can see that there would be 5 variables in total, the force, velocity, density, viscosity, and diameter. And among those variables, the 3 basic dimensions that each of them are founded on is length, mass, and time. And so there should be 2 dimensionless groups that's going to predict the behavior there. And so what we have to do is we need to predict this by identify all the variables that are significant. Okay, we've done that. List the variables and dimensions in a table, and then rearrange the variables so that there's a dimensionless group is developed. And so I'm going to do this on the whiteboard, and so that you can follow along if you're watching the video. I'm going to turn the screen off because I don't want to spoil it. You know, I don't want to do a spoiler alert here. I'll put it here. All right. So write this in your notes. It'll be useful later. We've got force, which we know variable F as units of newtons. And so newtons is kilogram meter per second squared, and that is mass, length, and time squared. Okay, velocity is one of these parameters that affects drag of a sphere as it settles. Velocity is meters per second, which is length per time. Density is kilograms per cubic meter, and so that's mass divided by length cubed. Viscosity is newtons seconds per meter squared, and a newton is a kilogram meter per second squared, so there's the newtons, and so then we still have to have the seconds from the seconds, and then the meter squared is there also. And so that reduces down to kilograms divided by seconds times meters. And so that's mass divided by time times length. And then finally, we've got diameter. Diameter, or D, is in units of meters, which is length. Okay, so there are 5 variables. N is 5. M is 3, so that means we should have 2 pi groups out there. And I'm going to put together a table where we have the variables in one column and the units associated with each variable or variable group in another column. Okay. So the variable is force due to drag, velocity, density, viscosity, and diameter. And then I'm going to write the grouping of the units. So force is going to be mass, length, times squared. This velocity is length per time. Okay. The density is mass divided by length cubed. Viscosity is mass divided by length times time. And finally, diameter is length. Okay, so we're right now, step 1 is where we're at, just sort of the original given information. Here's our objective. We want to combine variables together to start canceling out units. Remember, we're trying to form groups of these variables that are themselves unitless. So some combination of variables that doesn't have any units. And so what you can do is think of beginning, what's the most simple variable we've got in terms of its units? The diameter only has units of length. And so what I'm going to do as I go from the first step to the second step is I'm going to use D, because I'm going to use D kind of like as a tool to cancel out units of length in other places, in other variables. And so here in the second grouping, I'm going to have the variables again. So I'm going to have the variables, and I'm going to have the units. Now, in the second step, I'm going to use D to cancel out any place the length is found. And so how do I have to combine F and D together to get the length units to cancel out of F? If I have F divided by D, then the resulting combination of units is just going to be mass divided by time squared. So look at what I did there. I said diameter has units of length. Length is in the numerator of the force variable group. And so if I have force divided by diameter, that cancels out the length parameter from the resulting combination. And I'm trying to simplify the units. With each step, I'm trying to make the group of units eventually to be unitless. And so I've accomplished that. So what should I do with V and D to cancel out the length parameter? V divided by D. Same thing as before. Right. So then what's that going to leave? What is the units of V divided by D? 1 over T. All right. Now let's see. Here we've got the viscosity, which has oh, you know what? I wrote the wrong units for viscosity. No. Density. I skipped over density. All right. So density has length cubed in the denominator of its units. And so how should we combine D and density together? Multiply. Cubed. Good. So if I have density times diameter cubed, then the resulting units of that is just mass, which is great. That becomes a tool that I can use to cancel mass in other groups. Okay, and then now to viscosity. Viscosity times diameter, the resulting combination there will just be mass divided by time. And then I just leave it blank for D. Like D is used up now. I don't have to put anything else in that row because I've interjected D into each of the remaining other variable combinations. I'll just, nothing. Okay, step 3. Now, by the way, I'll mention that there's more than one right way to solve a problem like this. There isn't just a single solution to these pi group constructions. So from 2 to 3, my strategy is going to be, what's the most simplest unit that's out there right now? It's just this combination of density times diameter cubed, and that gives me mass. So I can use that group of variables to cancel the mass unit out of other rows. Okay, so from 2 to 3, I'm going to use density times diameter cubed. All right, so specifically, what should I do? We've got the variables and the units. Okay, so how does that relate to F divided by D? Right now it's got mass in the numerator, so I'm going to have F divided by density diameter to the 4th, and then the resulting units of that will just be 1 divided by time squared. Okay. Does everybody see that step, the logic of it, why we did it? Okay, now what do I do in this next row, V divided by D? Well, there isn't any mass term there, so it carries through. I'm still left with V divided by D, and it still has units of 1 divided by T, okay? Now, this is the one that I'm using, so I just put a dash there. It's used up. And then finally, U divided by D is mass divided by time, and so I need to have UD divided by density D cubed, so that's going to cancel the D in the numerator with a D in the denominator, so it's going to end up with viscosity divided by density times diameter squared. Yes?
With Huffman, did you take the square root of the whole thing and get like whatever sheet?
Yes, you could, but we want to have it be T, or actually unitless, not just T by itself. I think we'll be able to do it even simpler than that. Okay, so we've got a step 4 because we're not yet to unitless. These groups still have dimensions. Oh, by the way, so the units of this one is 1 divided by T. So we've got 3 groups. We know that in the end we should have 2. We should have 5 minus 3, so we should have 2 groups. The other clue that we're not done yet is that these 3 groups still have units of time that needs to be canceled out. Okay, so let's use my suggestion from step 3 to 4. There's more than one right approach here, is let's use V divided by D to cancel out units of time. Okay, so how would we combine that? Well, we would need to multiply by the inverse of it, and we need to square to do this here in step 4. So we've got variables and the units associated with those variables. So it's going to be F divided by density, velocity squared, diameter squared. So we basically are flipping V divided by D and multiplying it by it twice. So we had D to the 4th. Now we've just got D to the 2nd because 2 D's from here went up to the numerator. And then we now have velocity squared in the denominator. So that becomes unitless now. That's one of them. Now this one is the one we're using, so it just becomes a dash. But then how do we integrate this one down into here? That's the same thing. It's going to be the inverse of it. So it's going to be viscosity divided by density, velocity times diameter, and then that's also unitless. This is some nutty stuff, right? Like this is a Sudoku puzzle, or I don't know, a brain teaser. But it's important for you to get some practice with that. And so I've prepared a handout, and I'm going to ask you to try this out on a similar approach. Now, let me bring this up on the screen in case you can't quite see my chicken scratch scribble on the whiteboard. Maybe this chicken scratch on the projector will be easier to see. Wait for it. Yeah. The only way it starts making sense is to try it for yourself, really, to try and solve it and check with a friend on how it's going. All right, so let me give you this handout. There's two parts to it. First of all is just to reacquaint yourself with what the dimensions are of a couple of different expressions. But the real heart of what I'd like you to work on is problem 2. So we've got plenty of time to do this, and then I'll be circulating around with the solution, and I'll put the solution up on the screen. We've just got a few minutes left.
So you don't have to do the same thing to each board, you just have to use the variables.
Okay, so here's the solution. Now, not the solution. I put it the wrong way because there's actually more than one solution. Because just take, for example, our first step. If we want to start canceling out units of length, then there's H1 has units of length. Diameter has units of length. This other diameter has units of length. And so you could use any one of them to start canceling out the L in the other ones that remain. But in the end, when you go through all the combinations, you're going to have 4 pi groups, and I put a couple of the combinations at the bottom of the page there. And so what this process tells you is the variable combinations that would exist in the equation. And so it would give you a guide, for example, of data to graph. Like if you're going to be visualizing data of the experimental results. Question?
The last step, what happened to your D cubed?
D cubed.
Like this D.
Oh, yeah. I think it should be D cubed. And so does it remain? Oh, okay. Yeah, D squared in the top. That's where it goes. Yeah. So it should just be D. Got it? Okay. Yeah, for a second there, I wasn't seeing it myself. Okay. Well, we've got 6 minutes left in the semester, so I guess we should all just sit and stare at each other for the next 6 minutes. Make it a very awkward, uncomfortable silence. Run the clock out. That's what you did in elementary school, right? Before the end of the year? No. Let's just double check on these announcements here that we're all on the same page with the final exam. Okay. So it's going to be in this room. It's going to be on Thursday the 14th. Anybody in the marching band in here? The marching band is leaving on Thursday morning for the bowl game that Marshall's in. So people who are in the marching band have to kind of rearrange their final schedules a little bit. So it looks like we won't have to work with that issue. 10:15, 12:15. I provide the equation sheet. I provide the exam. You provide the knowledge. Okay? The good attitude, the positive mental attitude. Don't stay up all night studying. It's just not worth it. All right. Have a good day.